Right. Hey, I'm Jasper. I'm going to be talking about a paper by Karl Bringmann and myself where we look at subgraph isomorphism. Our paper contains quite a few results on this, but I'm going to be focusing mostly on our main result, which is that you basically can significantly improve on the currently known algorithms for subgraph isomorphism for bounded Treewidth pattern graphs under certain hardness assumptions. Okay, so a quick recap on the subgraph isomorphism problem. So in this problem, you're given a pattern graph H, which is usually quite small, and a host graph G, which is usually quite large, and you want to check if you can find a subgraph of G, which is isomorphic to your pattern graph H. Okay, and there are lots of interesting parameters you can look at for this problem, but one of the most interesting ones is the tree width of the pattern graph. So we assume that our pattern graph has some constant size k, and that its tree width is also bounded by some t. And the way you should think about this is that k is much larger than t, so the tree width of our pattern graph is comparatively small. This kind of problem comes up often in practice. Okay, and what do we know about this problem so far? Well, there are two well-known bounds. The upper bound comes from the color coding algorithm, which you might know, and it basically tells you that you can solve this problem in time O tilde of n to the t plus 1. And the lower bound comes from a paper by Daniel Marks, and it says that assuming the exponential time hypothesis, you have that for any class of graphs of unbounded tree width, no algorithm can solve subgraph isomorphism for pattern graphs from that class in time order of n to the small o of tree width divided by log tree width. Okay, and if you look at this, you can see that there's still quite a gap between the upper and the lower bound, right? So, of course, the aim is to close that gap in some way, either by improving the algorithm or by improving the lower bound. Okay, and we do the latter, namely, we show that there exists a strict lower bound for the color coding algorithm. More specifically, we show that there exists a maximally hard class of pattern graphs, meaning that the subgraph isomorphism problem cannot be solved in time order of n to the t plus 1 minus epsilon for pattern graphs from that class under certain hardness assumptions. And let's quickly talk about those hardness assumptions. So our central assumption will be the hyperclick hypothesis. Okay, and what does that mean? Well, in the H uniform K hyperclick problem, you're given an H uniform hypergraph G, and you want to determine whether G contains a K hyperclick, so a set of K nodes, such that for any subset of size H of those nodes, they form a hyperedge in G. Okay, and for the purposes of this talk, we're actually going to always assume that H is equal to 3, but in general, you can formulate the H uniform hyperclick hypothesis as follows. There does not exist an algorithm which solves the K hyperclick problem on H uniform graphs in time order of n to the k minus epsilon for any k which is greater than h. Okay, and this obviously only works for h being at least 3, because for h equals 2, you have the standard click problem, which can be solved in time order of n to the omega divided by 3 times k, right? This hyperclick hypothesis is a relatively new hypothesis, but it seems to be both believable and useful. So there's been some recent work in geometric complexity theory which seems to point toward the fact that the hyperclick hypothesis may be true, at least in the algebraic world. And it's also been used in several other lower bounds, which you can find cited in our paper. Okay, so now that we've seen our hypothesis, let's go ahead and state our main result. There are actually two of them. The first one is under the 3 uniform hyperclick hypothesis, and the second one is a slightly weaker result under the strong exponential time hypothesis, so Seth. Okay, so let's go through them one by one. So in the first one, we prove that assuming the 3 uniform hyperclick hypothesis, we have that for each Treewidth, which is at least 3, there exists a hard pattern graph of that Treewidth, meaning that you cannot solve subgraph isomorphism for that pattern graph in time order of n to the t plus 1 minus epsilon for any epsilon. And now for the second statement, assuming the strong exponential time hypothesis, we can show that for all epsilon greater than 0, there exists a t which is at least 3, and a pattern graph h of that Treewidth t such that subgraph isomorphism on that pattern graph cannot be solved in time order of n to the t plus 1 minus epsilon. And what this means is that as the Treewidth gets larger and larger, we get closer and closer to a required running time of order of n to the t plus 1. All right, so those are our two results, and in this talk, we're gonna actually prove the first result here. Okay, but before we do that, we have to talk about the colored variant of the subgraph isomorphism problem, because it's what we use in our proofs. Okay, and what is the colored variant? Well, in this colored variant, you have that the pattern graph H is colored using k colors, so each node has one color, and G is also colored using those same k colors. And you have this additional constraint on your solution that the isomorphism must preserve colors. So you can group the nodes of G according to their color, and the problem now becomes that you have to select one node from each group such that if 2 nodes are adjacent in H, like here, then the 2 nodes that you selected from those 2 groups must also be adjacent, right? Right, so this is the colored variant, and you can define something quite similar for hyperclick too if you want. Okay, and why are these colored variants important? Well, it turns out that colored and uncolored subgraph isomorphism for bounded Treewidth pattern graphs are basically equivalent. The first direction of this was known. It can simply be shown using color coding. And the second direction is something that we prove in our paper. And what we do there is we basically attach a signature graph to each vertex of our pattern graph, which encodes its color. And as long as the Treewidth of the original pattern graph is at least 2, this will preserve the Treewidth of the pattern graph. Okay, and also it's easy to see that the uncolored and colored hyperclick problem are the same, because you can basically recycle the proof that uncolored and multicolored click are equivalent. Okay, and now that we've seen that the colored and uncolored problems are equivalent, we can use the colored problems, which are much more structured, as a basis for our reduction. Okay, so let's actually do the proof. So we're going to start with a 3 uniform 3 times t plus 1 hyperclick problem, colored, and the reduction is actually surprisingly simple. We'll be doing it in 2 steps. So in the first step, we're going to be replacing hyperedges by these auxiliary vertices. And to do that, for each triple of vertex groups in our colored hyperclick instance, we're going to start a new vertex group in our new instance here. Okay, and this new vertex group will have one node for each hyperedge, which was connected to exactly one node from each of the vertex groups here. So here, we have a hyperedge. So we create a new node here, which is connected to these 3 vertices here. So here, here, and here. Okay, and now via the pattern graph of this new subgraph isomorphism instance that we're constructing here, we will enforce that the node that we select here will have to be connected to each of the nodes that we select here, here, and here. So our pattern graph will look as follows. We will have one node in our pattern graph for each vertex group here, and also for each vertex group out here. And these will be connected by an edge if and only if this node here was part of the 3 vertex groups which were used to construct this vertex group up here. Okay, and it's now not hard to see that these 2 instances are equivalent because the pattern graph over here encodes the exact same constraints as the hyperclick edges over here. So here you have that for each triple of selected vertices, you have to have a hyperedge connecting them. And over here, it's that for each triple of selected vertices, you have to have a node from out here, which is connected to all 3 of them. And you have this one-to-one correspondence between the nodes here and the hyper edges over here. So they encode the exact same constraints. One more thing to note is that each of these vertex groups up here has size at most n cubed, because there are at most n cubed hyper edges between 3 vertex groups of size n. So that was step 1. We've just gone from a hyperclick instance to a subgraph isomorphism instance, but the tree width of the pattern graph of this new subgraph isomorphism instance is actually still quite large, and in step 2, we're going to make that smaller. Okay, and to do that, we're going to condense these vertex groups in the middle. And to do that, we're going to begin by dividing these vertex groups into sets of 3s. And for each such set of 3 vertex groups, we will create a new vertex group in the new instance on the right side. And we're going to have one vertex in this new vertex group over here for each possible choice of choosing one vertex from each of the 3 vertex groups over here. So in particular, that means that our new vertex group over here has size at most n cubed 2. Okay, and one node up here is connected to one of the nodes from the new vertex groups if and only if all of the edge constraints between its respective vertex group out here and all of the vertex groups from this set here are satisfied. Okay, and in the pattern graph, we have that one node out here is connected to one of the inner nodes if and only if um, the same vertex over here was connected to at least one of the three vertices here from which we constructed this vertex group over here. So here, these two would be connected because this vertex here would have been connected to both of these. So these two are connected, and because these would have also been connected, these are now also connected. Okay, so that's how the reduction works. It's more or less easy to see that the new instance encodes the same edge constraints as the old instance. We've just condensed the central vertex groups. So before we had 3 times t plus 1 central vertex groups, and now we have only t plus 1. So we've now gone from a 3 times t plus 1 hyperglyph instance to a subgraph isomorphism instance, and we still have to show that the Treewidth of this new pattern graph, which we constructed, is low. Okay, so here's how our pattern graph looks. So we have t plus 1 inner nodes, and each of these outer nodes is connected to at most 3 of the inner nodes. Okay, and we're going to show that the Treewidth of this pattern graph is exactly t. Okay, we're going to do that via the cops and robber characterization of Treewidth. So we have t plus 1 cops, which we can put on the graph, and we want to catch a robber. And what we can do here is that we can place our t plus 1 cops on our central nodes here, and then no matter where the robber starts, they will be surrounded by cops. And because we have that t is at least 3, we know that there exists at least one central node which is not adjacent to the robber. Right, so that means that we can use the cop from here to catch our robber here. Okay, so we've shown that t plus 1 cops are sufficient to catch a robber on this pattern graph, which means that the Treewidth is at most t. Okay, so let's summarize. We've gone from a 3 times t plus 1 hyperglyph problem with n vertices per group to a subgraph isomorphism problem with n cubed vertices per group, and the Treewidth of the pattern graph for this new subgraph isomorphism instance is t. So all that remains to show is that this reduction implies that there cannot be an order of n to the t plus 1 minus epsilon algorithm for subgraph isomorphism for pattern graphs bounded by Treewidth T. And we're gonna show that now. So if you assume that there exists such an algorithm, then that implies by using that big N is equal to small n cubed, that you have an order of n cubed to the t plus 1 minus epsilon algorithm for hyperclick. And if you just rewrite that, then you get an order of n to the 3 times t plus 1 minus epsilon prime algorithm for hyperclick, which can't exist under the hyperclick hypothesis. Okay, so that's it. We've shown that assuming the 3 uniform hyperclick hypothesis, there exist maximally hard pattern graphs for each tree width, such that subgraph isomorphism with those pattern graphs cannot be solved significantly faster than order of n to the t plus 1. So basically, you cannot beat the color coding algorithm. Okay, so now you've seen the main result of our paper, and I'd like to conclude the talk by giving you a super quick overview of the other results. Okay, so for example, we don't just look at bounded tree width pattern graphs, but we also look at bounded path width pattern graphs. And there we show almost tight upper and lower bounds. And in doing so, we actually show that you can use rectangular matrix multiplication to slightly speed up the algorithms in this setting. We also look at a weighted variant of subgraph isomorphism, and there we show basically tight bounds for several settings. And when showing the lower bound, we actually construct a kind of cool reduction where we modify the proof from this talk by using something called k-average free sets to encode certain edge constraints purely in node weights. There's also the result on colored and uncolored subgraph isomorphism being equivalent, and we show that this is the case for most of these settings that we examine. Okay, and the last thing that I want to mention is that we didn't just show a reduction from the hyperclick to the bounded tree width subgraph isomorphism problem. We actually also showed a reduction in the other direction, which actually shows that these two problems are equivalent in some sense, and in some way this also gives some intuition for why the hyperclick hypothesis might be the quote-unquote correct hypothesis to look at the bounded tree width subgraph isomorphism problem with. We also have a few more results in our paper, so if you're interested, you can read that. All right, yeah, that's it. Thanks for listening.